Howdy, today on Flippin Science we're looking at calculating Q and delta H. So there's two equations that we're going to use today, actually three because we're going to figure out the number of moles a bit later on. But let's just talk about briefly what these are. So the Q equation here, Q equals m times C times delta T. This is used to figure out how much heat energy is being transferred into or out of water. The delta H equation down here is used to figure out the molar enthalpy of a reaction. And we can see, since Q substitutes in here, delta H is equal to, if I do equal to, it's equal to my mass times the specific heat of water times by the change in temperature, and that's divided by the number of moles. So we can substitute in Q into this equation to see these terms. Let's have a look at what these terms mean. So Q, that's the amount of heat energy that's being transferred, like I said before, and that's being measured in joules. M, this is the mass of water, or it could be another substance, but we're going to look at it as if it's water. It's the mass of water that's being heated up, and that's measured in grams. So 1 milliliter of water is 1 gram of water most of the time. So 1 mil, 1 gram. So that means 150 mils would be 150 grams of water. 1 liter would be 1,000 milliliters, which is 1,000 grams of water. C is the specific heat of water. Again, this could be a different substance, but usually it's water. What the specific heat is, it's the amount of energy to raise 1 gram of water by 1 degree Kelvin. And that gives us our unit here. So our unit is joules per gram per degree Kelvin. So this is the amount of energy required to raise 1 gram of water by 1 degree Kelvin. And it's 4.18 joules per gram per degree Kelvin. This might be shortened down to 4.2 depending on the question that you're given. So to raise 1 gram of water by 1 degree Kelvin, it's 4.18 joules of energy. A degree Kelvin is the same magnitude as a degree Celsius, it just starts at a different place. Delta T up here, this is our temperature change, and that's measured in degrees Celsius, so our final temperature take our initial temperature. I've expanded the equation down here, the delta H equals Q on N, because this is the one you're given. I've expanded it to put the Q values in here. The only addition here is now to find the enthalpy change, which is delta H. That's the amount of energy released per mole of reactant. So that means we need to take our energy being transferred and divide that by the number of moles of reactant. So that's the number of moles down here, and that's the unit there. So the enthalpy value is how much energy is released or absorbed per mole of reactant, and that's how we figure it out. So the best way to learn how to use these equations is to use some experimental questions. So here's my first question, and here's the setup for the first question. We are burning 0.34 grams of methanol in a spirit burner. So here's my spirit burner down here. It's generating heat that's heating up some water. We're measuring the change in temperature of the water by using a thermometer. We've got 150 mils of water in the beaker that we're heating up. Down here it says 0.34 grams of methanol is burnt. The way that you figure that out is you weigh the spirit burner before you heat up your water, then you weigh it after and you subtract the final from the initial, and that tells you how many grams of methanol that you burnt. The temperature change of the water, we've got the initial temperature here is 18, the final temperature is 25. And down here we have the specific heat of water. Now in this question it says specifically to use 4.2 joules per gram per degree Kelvin as your specific heat is water. So we're going to use that when we're doing our calculations. So the first question is calculate the heat energy in kilojoules absorbed by the water in our system. So let's do that. So because it's asking for the heat energy being absorbed, that's a Q value. So we're going to use our formula here, Q equals mc delta T. So let's have a look at our bits here. So Q is equal to our mass. Now our mass, remember, that's the mass of water that we're heating up. In this case, 150 mils of water is being heated up, so that's 150 grams of water. We're going to multiply that by the specific heat of water, which in this case we're using 4.2. And then we're going to multiply that by the change in temperature. To figure out the temperature change, we need to look at our initial and final values. So for any change, and we use the symbol delta to represent a change, you do the final value minus the initial value. So it's going to be 25, which is my final value, and from that we're subtracting away 18 degrees. So 25 take 18 is 7 degrees Celsius, so we're multiplying here by 7. 7 degrees Celsius is 7 degrees Kelvin. So let's calculate the answer. So I put it in my calculator, 150 times by 4.2 times by 7, and that's 4,410. Now the question is, that's my quantity, but what's my unit? And the way to figure out the unit is you look at the units that you use for the bits and pieces that you've got together. So our first unit we're looking at is mass. Mass is measured in grams. That's being multiplied by the unit for specific heat of water. So that's joules divided by grams multiplied by degrees Kelvin. And then we're multiplying that by 7, which is our degrees Kelvin, because it's temperature. So now we can cancel out the values that are the same on top and the bottom. So get rid of that. Get rid of that. So I've got rid of my 2 degree Kelvins, get rid of my grams, get rid of my grams. And I'm left with joules. So the unit for this one is joules. Now the question asks specifically for kilojoules, so we need to divide that by 1,000. So we get 4.4. Now look at our significant figures, 2 significant figures in the data here, 3, 2. So we're going to go to 2. So 4.4 kilojoules. And there's our answer for the first part. So the second part of the question asks you to calculate the molar enthalpy of combustion of the methanol in kilojoules. So let's do that now. We're going to be using this expanded version of the equation here. So remember, Q is m times C times delta T, so the mass times the specific heat of water times the change in temperature. So if we substitute that in here, then all we need to add is a division by the number of moles of reactant. And we can calculate that by using another equation, N equals m on m. So this is number of moles is equal to the mass divided by the molar mass. I've got other videos that go through this if you want to have a look at it. So let's calculate our number of moles. So we've got 0.34 grams, so that's our mass. So 0.34 grams of methanol, and we need to divide that by the molar mass of methanol, and that's going to be, we need to figure out what methanol is. Methanol is CH3OH. Again, if you don't know this, you can watch my video on organics. Our molar mass there, we've got 1 carbon, which is 12.01 grams per mole, 4 hydrogens in total, so plus 4 times 1.008, because that's the molar mass of hydrogen, and plus a 16 for the molar mass of oxygen. And we can calculate that over here. Let's do that. Chuck it in my calculator. So we've got 0.34 divided by big bracket, remember to use the bracket, 12.01, plus 4 times 1.08, plus 16. And I get 0.0106 moles. I'm going to keep that value in my calculator because I'm going to use that when I calculate the delta H in a second. So let's go back, and now we've got all the information we need to calculate delta H. So the enthalpy change. So delta H is equal to our mass of water. So the mass of water was 150 grams from 150 mils, so 150, times by our specific heat of water, which was 4.2, which is down here. Timesing that by, multiplying that by the temperature change, which was 7. So this is the same as what we used before. Then we're dividing that by our number of moles, which is, use the right colour, 0.0106 moles. So now I'm going to pop all this in my calculator. I'm keeping the value down here that I just calculated, so I'm going to put brackets around the top line here, and I'm dividing by my answer. So open bracket, 150 times by 4.2 times by 7, and I'm going to divide all of that by my answer from before, and I get, if I write it down, so delta H is yellow, equals 41560, and if I round that off to the nearest number, 4. Now I need to figure out what my unit is. My unit for here before I divided by 1,000 was joules, and this is in moles, so my unit then is joules per mole. Number of moles is in moles. The answer asks specifically for it to be in kilojoules. So to turn from joules to kilojoules, we need to divide by 1,000. And so divided by 1,000 on my calculator, really I'm just moving this decimal place a few times, and I get 415.6 kilojoules per mole. And I need to look at my smallest number of significant figures, and I think it's still about 2. So my smallest number of significant figures there is 2, so it would be 420 kilojoules per mole, if I finish that off like that. Okay, so there's an example of one type of question like this. The second question is a little bit different. We've changed a few things, so we're going to be burning butane instead of methanol. We're burning 1 gram. Butane is the gas found in cigarette lighters. The chemical structure of butane is down here, so we can use that to figure out our number of moles later on. Our specific heat of water has changed to 4.18 joules per gram per degree Kelvin. We've been given the delta H value. We're heating 1 litre of water instead of 150 millilitres, and we're given the initial temperature. Our job is to find the final temperature of the water. So to find the final temperature, we need to rearrange our delta H equation over here to make delta T the subject of the formula. So let's do that now. So we've got delta H is equal to the mass of the water times by the specific heat of the water times by the temperature change, and that's all divided by the number of moles. So the first step is we need to get this number of moles over here. So we're going to multiply both sides by the number of moles. So, and then I'm going to move everything over this side too. So I'm going to have my delta T over here times by the mass times by the specific heat equals my number of moles times delta H. So number of moles times by delta H, which is yellow. Here we go. There's an H, okay. Now we need to divide this side, both sides I mean, by the mass times the specific heat. So let's do that. So if I do that, I'm left with delta T equals my number of moles times by delta H divided by the mass, which is green, times by the specific heat of water, which is blue. Okay. Now, we've got a little bit of a conversion to do. My unit for specific heat is in joules, but my unit here is in kilojoules, so I need to turn this back into joules. So I times that by 1,000, and I get 2874000 joules. So I need to use that number when we're over here, otherwise we'll have an error. Okay, now that we've rearranged it, we can shove in our values, but we need to calculate our number of moles. So I'll just use one colour here. So number of moles we had before is mass over molar mass. So my mass is 1 gram. My molar mass, 1, 2, 3, 4 carbons. So putting that in brackets, 4 times 12.01, the molar mass of carbon. Plus pi, there's 10 hydrogens there, 10 times 1.008. Okay, times by the delta H value, we're using this 2874000. I'll use the same colour, 2874000. And all of that is divided by our mass of water. 1 litre of water is 1,000 grams of water, 1,000, times my specific heat, which is 4.18 joules per gram per degree Celsius. Okay, so I'm going to put that in my calculator. I've got 1 divided by, I'm going to start with this section, open brackets down here, 4 times 12.01 plus 10 times 1.008 equals, we're going to times that by the 2874000, so my delta H equals, divide that answer by, open brackets, 1,000 times by 4.18. Okay, press equals and I get 11.83 degrees Celsius. Okay, so that's my temperature change. I need to figure out my final temperature. So my temperature final, we started at 18.5. We need to add on to that the 11.83. This is an exothermic reaction. It's giving off heat energy, so the temperature of the water is going to increase. So if I add 18.5 to my answer, I get 30.33 degrees Celsius, which is 30 to 2 significant figures, which is probably too much, so 3.0 times 10 to the 1 degrees Celsius. Okay, but I'll just keep it as 30 for him. Okay, so today on Flipping Science we saw how to use the Q formula and the delta H formula, as well as rearranging the delta H formula to figure out its final temperature. That's it for Flipping Science today. See ya.